Okay, guys, as promised from our last on-campus visit, and Alice, with you missing that class, I think this is going to be really good for you as well. But I could tell after the meeting that it was going to be really good for us to sit down and do an ANCOVA design from start to finish, and I intend to go through everything from checking assumptions, running the analysis, converting to to type 3 sum of squares calculation method. I'm going to show you how to do effect size. I'm going to show you how to do pairwise comparisons, and I'm ultimately going to show you how to write up the results, which I think is what most of you want. So this is going to be a nice presentation for kind of a overall. There you go, Bobby. Dinging. That was my phone, I do believe. So anyway, let me explain what I've done. I've set my working directory, just as we always do, and saved my data as data and attached it. So all is cool there. Now, what I want you to think about is a situation where we have. Let's concentrate on group here, and let's say that we have some math professors at Shawnee State get together, and they think that there could be a better way to present instruction to Math 1500 at Shawnee. So let's say that Group 0 is typical lecture instruction using my stat lab, and let's say that Group 1 is typical instruction, lecture using Stats Portal, which is another online course management system in competition with my stat lab. And let's say that the group number 2 is typical instruction, but using R as a statistical software package instead of using the online course management systems. Now, you guys seem to be, on top of this. Looks like we got a sample size of 51, and I think we would clearly off the bat. Let's go group. So let's do type of instruction. So guys, right off the bat, I think you guys would realize that you've got to set the group as a factor. This is categorical, category, categorical, in that there's 3 different group types of instruction, and so we need to set it up as type. Okay, nothing brilliant there. Final is just as you would think, the final exam score, and I copy and pasted these from a semester, well actually last semester, spring, and I hunted up their ACT scores. Now these groups over here are fictitious. Fictitious. They're made up. They're artificial, right? We didn't conduct this study, but all right. There's my dog. Don't you love it? The AC, there's going to be a lot going on today because I've got a lot of activity going on outside. So my dogs are going to, well, my dog. Seems like I have my neighbor's dog because it stays here all the time, but my dog will be going insane. So get prepared for the for all the barking. Plus, have good friends who are in China right now adopting a little girl. They are leaving for their province here in just a few minutes. So Facebook's going crazy on posts about that. So, guys, anyway, final and ACT are real measurements. They are really true measurements from students at Shawnee State. The group is not. Now, as you would expect, the first thing we'd want to do is look at some descriptive statistics. And I'd want to look at a histogram of ACT. And that makes me smile. I have no reason to think that the normality assumption is violated. Okay. I'd also want to look at a histogram of final. And that makes me smile as well. I'd probably also want to look at a box plot of ACT. And you can see right up here we have an overachiever, big old, I don't know, a 35 or something. I mean, we could find out certainly if we needed to. And let me show you how to do that just while we're at it. If I do sort ACT, it puts it in lowest to highest, so the outlier would be the person with the ACT of 33. So I also want to do a box plot of final, and that again makes me smile. Very, very, very happy with that. Now the next thing I'd want to do is I would want to get my descriptive statistics across type of instruction, and we should know by now that we do t-apply, and so I want to run that over ACT, over type, and I want to do the mean. Now guys, up to now I've always done fun equal mean, all caps. I've found that this upgraded version of R, that we don't have to do that. So gang, there's the t-apply for ACT over type, giving the mean, and I'd obviously want to do this again for the standard deviation. And I'll report those in the write-up. So guys, you'd want to go ahead and do this for final. So both quantitative variables, you'd want to do this. Okay, so we're kind of ready to begin thinking about the ANCOVA. But remember, the ANCOVA has two. Well, let me back up a little bit. We've still got an assumption from the ANOVA part that we've got to take care of, and that's the potential violation of homogeneity of variances. So what I need to do here is I need to do t-apply final over type, and I'd want to do standard deviation again. So it looks like let's see, the biggest variance for ACT is 5.23. Divide that by the smallest variance. Actually, we need to do this on final, don't we? Yeah. So the biggest variance is 19.39. And the smallest is 11.88. And we get 2.66, which is a violation of our equal variances. So, we just need to report that. Really the one that I would be most worried about would be in the covariate here. So, the covariate would actually be, 5.23 squared divided by 3.61. And 2.10. So yeah, we've slightly violated, but when we write this up, we'll let the reader know, and I'll tell you some things about that then. All right, so let's switch gears to the ANCOVA. Assumptions for ANCOVA. There's two major ones, and the first one is homogeneity of regression slopes, and the second one is we want independence of the covariate over treatment. And in this case, treatment is teaching styles, not teaching styles, teaching techniques. Okay, so we need to test those. Now, what I'm going to do first of all is I'm going to test the homogeneity of regression slopes. So I'm going to test that first. The easiest way to do this, and again, in previous videos, in the last video, I broke these down and looked at the regression slopes, looked at pictures on scatter plots. The easiest way to do this is to look at the statistical significance of the interaction. If the interaction is statistically significant, then we violate the homogeneity of regression slopes. If it's not statistically significant, then we don't violate that assumption. So I'm going to start this out with just fit 1 because we're going to be doing multiple fits throughout this. So I'm going to run ANCOVA, and I'm going to run my final over. I want to do my ACT as an interaction with, what did I call that, type. So summary, fit 1. Now here's a case where we're hoping we don't have statistical significance. And you can see that the p-value of 0.865 fails to reject the null. So guys, we're okay with the first assumption, the homogeneity of regression slopes. We're okay with that. The next thing we need to do is we need to look at the independence of the covariate over the treatment. So here I'm just going to run a standard ANCOVA of my covariate over type. Now again, I'm hoping that we don't have statistical significance, because if I do, I violate that assumption. And you can see that we have a p-value of 0.51 telling us that, telling you that the means across instruction level for our covariate ACT are not statistically significant. So there's no violation of the independence of the covariate over our treatment. Okay, so at this stage, both ANCOVA assumptions are not violated. So that's kind of good news. So we're ready to go ahead with the analysis. So let's do that. So what I would call this is, I would call this fit 3. And I would run the ANCOVA. And again, I'm wanting over the final exam. But I want to put in my covariate plus my independent variable. Okay? Make sense? Hope so. So I'm going to do summary fit 3. And this is what I get. Now, what's going on here? Well, this calculation is dependent on which way we put the variables in. If I had put type in first and ACT in second, there's a good chance that I would get different p-values. So what I need to do is I need to use the drop 1 function, like illustrated in previous videos, and in class. And what this gives us is it gives us the more traditional type 3 sum of squares calculation method. Now, yeah, not a huge difference. In fact, the p-value for the type doesn't really vary at all. You can see the f value is stable. But we do get a little different f value and a little different p-value. Now, in the broader scheme of things, both of these p-values are statistically significant at the 0.001 level. So there's strong support against the null hypothesis. So, what we got going on here is a couple of things. We've got non-statistical significance across the type, but we have statistical significance across ACT. Now, what does that mean to you? Okay, how do you write something like that up? So let's see. I'm kind of worried about what's going on out there. Okay, all right, guys. Let's first of all talk about the teaching techniques. So, whoever came up with this study had reason to feel that the lecture using my stat lab, or stats portal, and possibly R would lead to different results. And you know what? Just for the heck of it, let's just run an ANCOVA here. I'm just going to call this one my model. Let's just run an ANCOVA over final, just over type. And you can see we don't have statistical significance, so really coming in and controlling for the covariate, probably wouldn't lead to a difference in the type of instruction. But nevertheless, we're all teachers, and we all, if you think about who could you create the most gain with, well, that'd be the student with the most potential gain. So if you start out with a bunch of really, really high-level students, ending up with a high-level final mean may not be as impressive as if you started out with a group of, say, moderate math beginnings, moderate math level, and you turn them into the same mean. So that's what the covariate allows us to do. It allows us to go in and control for that effect and adjust the variation. Just the sum of squares, actually. So, when we put in our final model, let me highlight it. I've done something kind of out of whack here. I need to explain these. So the first thing I want to do is I want to tell you how I would explain the treatment. And this is the instructional technique. So what I would say here is I would say that the effect of varying instructional technique on students' final exam scores while controlling for entering math level by using math ACT subscore is not statistically significant, and I'd report my results. So I have an F test, so let's go back up to type, and we can see that our F value is 0.22. Our degrees of freedom are 2 for the type, and we have to go back to our initial ANCOVA to see that the degrees of freedom for the error is 47. So I would report this as 2, 47 equal the F value, which is 0.22, and my P value is equal to 0.81. So that's the way I would write that up. Now, how would I write up the covariate? So this is the ACT subscore, or the math ACT subscore. So what I would say here is something to the effect of, I don't know, probably I'd say something like the covariate ACT math subscore was statistically significant as related to okay, so let me make it come. I gotta be honest with you, I am my ADHD is kicking in. I'm distracted by this lawnmower out there, so say you probably are too. My ears are buzzing. All right, anyway, the covariate ACT math subscore was statistically significant as related to the final exam score. And I'm going to come in with my F, so my degrees of freedom were 1. Okay, guys, so what I'm doing, I'm going, lost my place here, where am I? Okay. Right here, so my degrees of freedom are 1, again over 47, and my F value is going to be 99.65. Okay, so back here, 1, 747 equals 99.65. You would think that my neighbors would know when I'm putting up a and actually, if I told them, they probably would wait. I got great neighbors. So anyway, I would say the covariate, which is ACT math subscore, was statistically significant as it related to the final exam score, and I would give the stuff. All right. So we've pretty much got that done. Now, another important thing that we would need to be able to do is we would need to be able to carry out pairwise comparisons. Now, you might sit there and think, well, why in the world do we need to do pairwise comparisons? Because nothing is statistically significant. You're right. In this situation, I would go ahead and carry out the pairwise comparisons, and I would report the results. But you're not going to get anything statistically significant. So for the most part, what I want to do is I just want to illustrate how we'd compare pairwise. All right, so wish me luck on this one. The first thing we'd have to do is we'd have to install packages. And I would install what's called MultiCop. Now, we got to go up here and choose a crayon, and I'm just going to choose that one. No reason, just damn. It's the one I usually choose. Now, you can see that the computer is doing some stuff. It goes through, some stuff. Now, once I do that, I would want to look at the library of MultiCop and go ahead and make sure that those are all loaded. And so, life is good. Okay? Well, I don't know if life's good yet, but we're going to find out whether life is good when we run these pairwise analysis. Now, at the end of the day, what we're doing here is we're doing contrast analysis. And we're testing all possible pairwise combinations. So we're going to have to create an interaction variable and go from there. So guys, wish me luck here. So what I'm going to do here is I'm going to start out with our data, which I have, $tall. And I'm going to run with data. And I want an interaction across type. Okay? Now the next thing I want to do is I want to run a linear model. Think more in terms of a general linear model. So I'm going to call this general linear model 1. Guys, remember general linear model, regression, ANOVA, ANCOVA, they all kind of meet somewhere because general linear model is just the general form of ANOVA meeting regression. So I'm going to run a linear model, and I want to look at my final exam score as it relates to my a covariate of ACT, and then I come in with plus tall. Okay, GLM1, linear model, final, ACT, plus tall, data equal data. All right, you got to tell it where the data is, dummy. Okay, so the next thing I want to do is I want to run what I'm going to call L1. And this is just going to give me my pairwise comparison, so it's going to just call it kind of a list 1. And I want to use what's called GLHT. And I want my model GLM1. And then I want to do linear factor equals MCP. Tall equals Tukey. Now I want to run a summary of L1. And I can see that I get my multiple comparisons. Now none of these turn out to be statistically significant. We look at these deals over here, these p-values, and nothing is even close to 0.05. But it gives us standard errors. It gives us test statistics, and it gives us of course our point estimate. But again, there's no statistical significance as we would expect. Now the next thing I want to do is I want to show you how to calculate effect sizes. Now, a little bit about effect sizes. As we're all aware by now, our test statistics are highly influenced by sample size. If we get a sample size large enough, we can increase our power and we can reject anything. So anything is subject to being statistically significant, in the realm of the p-value and this rather crazy 0.05 obsession that we seem to all have. I guess myself included. Actually, not myself included, but hey, this is just the way we teach it. Okay, so enough of that for now, but maybe a little bit more later. Anyway, effect size tends to come up with a way to control the measurement, the effect measurement, without the impact of the sample size. Now, the two most common effect sizes, one is Cohen's d, and Cohen's d, the way I want you to think about that is a Cohen's d of 0.2 tells us that the effect is small. Cohen's d of 0.5 says that we have a moderate effect. And Cohen's d of 0.8 tells us that we have a strong effect. I think of anything over 1, 1.1, 1.2 is very strong. There's another effect size that we report, R, and I tend to think of these, and guys, R, actually you have to think about these in absolute value. But anyway, think about these in absolute value. So if we have an absolute value of 0.1, it's hard to tell the difference. Okay, 0.1 or negative 0.1 would be a small. 0.3 would be moderate. And a 0.5 would equal a large effect. Now, how do we calculate these things in R? Well, we're going to have to install another package. So I want you to go install packages. And what we need now is called Compute ES. Or is it IS? It's either ES or IS. I don't remember. Daggone it. I think it's ES. Let's go for it. See what happens. Well, it liked it. I don't know if this is what we need, but it liked Compute ES. I'll tell you what. Let's look at this. I'm pretty sure this is it. Now that doesn't lend much support. Okay, I'm going to go for it. I think this was it. Now, let me show you a little trick. There's a function to calculate effect size for ANCOVA. We can use what's called A.FES. And to be honest with you, I don't remember what A.FES is all about. So I'm going to type help. I remember there's a lot of things we have to put in, but I don't remember what they are. So what I'm going to do is I'm going to read this. So I need my F value, and I need my treatment group sample size. I need my comparison group sample size. I need the covariate outcome correlation. Okay, the number of covariates. Okay, all right. So everything's pretty cool here. So what I want to do here is I'm going to copy that, and I'm going to close this down because I've got a pretty good idea of what's going on. Well, I need something before I do that. I need the correlation, don't I? So let's calculate the correlation between our covariate and our dependent variable. So got a high correlation here, 0.83. Okay, so now let's come in with paste. Now, let's go back up and let's first of all, and let me come in and do this. So we want the effect size for the covariate. Okay. Now, if I go back up to my type 3, which is, I've got too much going on here, guys. Here we go. My ACT, the F value is 99.6487. Now, my N1 was what, the treatment group sample size. So I had a balanced design there with 17 in each. My comparison group sample size was also 17. My correlation I just got was 0.825. And Q is the number of covariates I had, which is just 1. Data is data, and this actually should work. Okay, that's fun. Alright, let me see if I can figure out where I'm wrong here. So 99, that's good. 17, good. That's good. Level 0.95. I don't really care about all this stuff here. Let's see if this works. Okay, effect for ACT, VS, 99.65, 17, comma 17, 0.825, comma 1, level equal 0.95. Okay. For some reason, it didn't like that that data equal out here. I don't know, because if you notice, all I did was just delete that, and it works. Okay. So as I told you up here, we look for D and R. Right back here. Remember Cohen's D and R. So if we look at D, we have 1.93, which is a very, very, very strong effect. And if we come on down, it probably gives R as 0.7. So 0.7 on the R is above the threshold of 0.5, and then the 1.93? Yeah. According to Cohen's D, that's the one I always report. Is very strong. Now we're probably not going to get a very strong effect size for our treatment. Let's go ahead and run it. I think our F value for treatment was 0.22. Is that right? Go back and make sure. Yeah, 0.22. And let's get rid of all this stuff. And when we run the effect size here, we get D of 0.09, which back in the, I think what was it, 0.2 in the Cohen's, so 0.09 is extremely small. So guys, just not much going on there in terms of the effect size. So we've run our analysis, and I think our assumptions were solid, and we've run. At the end of the day, we found out that our instruction technique is not statistically significant, but ACT and final exam score are highly correlated. So now it would come time to write up the results, and I've already done that. because it took a while. But I'm not going to sit here and read this to you, but again, I say I one way, but okay, what am I doing? I'm sitting here reading to you. That's lovely. So see what I did in the first sentence or first paragraph is I just set up and tell the reader what I did. Introduce language, introduce the motivation, and just describe the variables that I've used. Obviously I want to distinguish what's my independent variable, what's my dependent variable, and what is my covariate. The first thing I do is I come in and talk about the categorical variables. Well, categorical variable, and give sample size in each. And then I present the means and standard deviations across the instructional techniques. I didn't do this, but I would have copy and pasted the histograms. Now what I would have done on the box plot is I would have done a side-by-side box plot. Let me just go back and make sure that we know how to do that. So I would have done this. I would have done a histogram of final across type. Oh, Doug, come on. I would have done a box plot across type. And then I would have copy and pasted this and inserted into the into the appendix. And I also would have done a box plot of ACT across type. Okay, and of course the equal variance assumption seems more plausible there, but we'll talk about that too. So I would have done that. I'll copy and pasted those and put those in the appendix. Next thing I do is just talk about the assumptions, and I go in the first first sentence. I looked at the interaction of ACT in class, and that indicates homogeneity of regression slopes. The next thing I looked at is the ANOVA of the covariate over instructional techniques, which indicates that we have independence of the covariate across instructional technique. Just go ahead and read this. Now, something really important. I do come in and talk about the homogeneity of variance assumption appears to be violated. So I've given you a couple of notes. Hopefully, when it comes time for you to do your master's thesis, your capstone project here, you're got to write this up and cite and do all sorts of cool stuff. But when doing this, you would need to cite from the literature that using the ratio of the largest variance to the smallest variance, and that being greater than or equal to 2, you need to find that in the literature somewhere and cite that that's an agreed upon measure. And you'd also need to cite Stevens or someone who found the results of I should say ANCOVA are tenable under the violation of homogeneity of variances. So a big couple things you'd have to cite there. This is kind of the heart of the matter. Isn't there a song, "The Heart of the Matter" by I don't know. We'll have to look that one up. So guys, notice I come in and report just what I did in R, but I also report the effect sizes. And I've also given you a note that when I say the value of the effect size indicates a very strong difference, you need to go into the literature somewhere. And I've got actually a textbook. It's called Tabishnik and Fidel. It's actually two ladies wrote a statistics. It's almost the Bible, obviously with a little b, of statistics. So you'd probably want to go to that text and cite, an interpretation of effect size. Okay, so guys, note 3, if there was a difference in instructional technique, you'd want to include a table that has the pairwise comparisons. Look at the point estimate, look at your test statistic, and report your p-value. In fact, I even think it would be a good idea even if you don't have statistical significance. All right, my dog's losing its mind again, which is nothing new. But anyway, that ends the video. Thank goodness. So you won't have to sit and listen to my dog barking. So, guys, have a good one.